Okay, good morning. So thank you very much for invitation. So, so today I will talk about the Coulomb branch for quiver gauge theory for symmetrizers, and plan of talk is, so I will separate my talk into two parts. The first part is a review of works of Hennenfent and Grassmannian there. And the second part is the main part, and this is definition of Coulomb branch for theories with symmetrizers. And this part is a joint work with Alex Weeks, who will come this afternoon. So I first record the definition of Coulomb matrix. I mean, of course, everybody knows. So C is symmetrizable Coulomb matrix. So which means that the diagonal entry is 2 and of diagonal entry is non-negative, non-positive integers, and there's integers, diagonal or integral matrices. Di is positive integer such that so di Cij is equal to Gj Cji, and di, this is called the symmetrizer. And for given such symmetrizable Coulomb matrix, one can associate Kac-Moody algebra. In fact, this symmetrizer is not necessary, but if you assume existence of symmetrizer, then you have invariant inner product on this Kac-Moody algebra, and various properties is nicer if you assume this existence of symmetrizer. So anyway, you can associate Kac-Moody algebra. And it has been known that Kac-Moody algebra, representation theory of Kac-Moody algebra, is closely related to representation theory of quivers. Quiver. So associated with this Coulomb matrix. So the relation is that, so you take quiver, so Q0 and Q1. Q0 is a set of vertices and Q1 is a set of arrows, and you forget the orientation of Q1 and consider the adjacency matrix, and the Coulomb matrix is defined as 2 times I minus A. So this is the adjacency. Or I forget the spelling. Maybe something like this. But from this construction only gives a symmetric Coulomb matrices. So symmetrics mean that Cij is equal to Cji, and I mean then it means Di could be arbitrary scalar matrix, but people usually take implicitly Di is equal to 1 because you don't make symmetrize if Ci is already symmetric. So the question is how to generalize question or problem. So how to generalize? General symmetrizable case. So this is the question. And this question is, I mean, very, as I mentioned, that this relation between Katz-Moody and representation quiver has some long history. So many people already asked the same question in the past. And we have many previous answers. So I just name only a few. So there is construction by using so-called species, and or also holding on quivers, and so on. And these constructions is compared with what are known for symmetric case. So this answers. This construction, there is part of relations, but not in full. So, for example, in this construction, it is not clear what is analog of quiver varieties. So people can understand, for instance, the analog of Gabriel's theorem, which is the starting point of this relation, can be generalized to symmetrizable, but we don't have. So this Hernandez-Leclerc, this is 2013, and Grassmannian, sure, this is 2000. So these are relatively new approach, and still, I mean, their construction is not really. Their construction are not really completed in the sense that they still have they don't have definition of analog quiver variety, but somehow they have some indication that their construction seems to going to right.
There exist analog of quiver varieties. Do you expect that there exists?
Well, I will come back at the end. And then our construction, the definition of Coulomb branch is motivated by their works. And in fact, the definition of Coulomb branch is really straightforward to generalize for symmetrizable. Okay. So this is really surprising that people thought that the definition of Higgs branch, quiver variety is an example. Higgs branch is easier, but in this particular question, the definition for the Coulomb branch is much easier. Okay. So what are their idea? So first, they put a modules Vi of truncated. Truncation is somehow technical, so I just take in place. Polynomial rings C of Gi truncated by Gi to the power Di. So for each I. So for in the usual quiver representation, we put vector space, complex vector space Vi. And so it can be considered that if Di is equal to 1, then this is just complex numbers, and you put just complex vector space. And point is, maybe this, So this I is correspond to this symmetrizer. And so in particular, so this Gi could be different for each vertex, but somehow related by this kind of relations. And then this is the first part, and the second modification is you have these modules Vi and Vj, and if two vertices are connected by oriented arrow, like this, then you assign, in the usual setting, you assign linear map, BH, between them. But in this setting, so we have additional map homomorphism given by multiplication of GI and GJ. Then we impose this condition, GJ of Fij times BH is equal to BH times GI to the Fji. And Fji and Fij is determined by Coulomb matrix. Maybe so I first consider Gij includes common divisor of minus Cij and minus Cgi. And Fij is ratio. So for this, the symmetrizers, information symmetrizers is lost, and symmetrizer appears only here. So this is, well, maybe I should not. So is it possible to read? Well, anyway, so the formula is not so important. Anyway, so we do impose this kind of relation.
Sorry, what is H?
H is arrow, index 4. And then guys look like they study the representation theory of this kind of algebra. So this is finite dimensional algebra, and it has various nice ring theoretical properties, which is very similar to the usual representation theory of quivers. And in particular, one of the main results, So they consider the space of constructible function. On the space of representation. As above. And then you can define the linear four algebra as usual. So that means that there is a definition of product and coproduct on this space. This is a Hopf algebra. And then they define the homomorphism from U of n plus of this Katsumudi algebra. N of Katsumudi, upper triangular part, universal enveloping algebra of the upper triangular part of the Katsumudi algebra to this space. This space. And which respects product and coproduct. And they show that this, I mean, if you replace the target space by those sub-algebra generated by the standard generators, EIs, then it is surjective. But they cannot, they conjecture that this is injective. So in that sense, I mean, some part is not completed. And also, they prove that if G is finite type, then this is isomorphic to the target.
Is it also true that intercomposable representations correspond to roots?
Yeah, that is already established. That is relatively easier part. They have a series of papers, and this is one of. But they don't. So far, they don't succeed to generate the quantum version. So in that case, they must replace this by how to say perverse sheaves on the space, and this such part is not. They didn't succeed. And Hernandez-Leclerc, in fact, Hernandez-Leclerc is first, and so they first studied, they first considered the preprojective and graded versions of the above. And in fact, but historically, they first find this version, and then just forgetting the arrows in the opposite direction, forgetting the grading, they get this GLS arrive at these representations.
What did you say was the result they wanted to get with the perverse shifts?
So this just.
I see. But if you just do everything over finite field, then somehow don't you get? So if you
Still they cannot do. So I just draw the quiver in this case. So I consider the B2. So in this case, we have BH and BH bar, and we have G1 and G2, and we have G2 square. BH is equal to BH G1 and G1 BH bar equal BH bar G2 square, and they draw the following quiver. And graded means that somehow, how to say, so this is it's a kind of the fixed point in the sister action, natural sister action, which multiply the edges. So you have this kind of arrows in. So this is a graded version of BH and BH bar, and then for let me see, maybe it's a little bit more complicated.
So is it important so you have two arrows between these two vertices, and you choose orientation such that one arrow goes another way, the other way, one way, the other arrow goes the other way. So is it important, or?
What do you mean? But the power part.
I'm talking about the orientation, the quiver. It's, or are you doing the version when you have sort of both arrows in both directions?
Arrows in both directions. So this is preprojective version.
Preprojective. I see.
Like this, and for the second one, so it goes in just one step up. This G2 just goes one step up, but for G2, this is G2, and G1 goes two steps up. Like this. So they consider the representation of the of this quiver. So I don't write the usual preprojective relation, but and also it is coming from the natural potential for this quiver. Come from.
Can you write down the potential?
So you have natural triangles and.
Okay.
Then main result of Hernandez-Leclerc. So they consider the Euler number of quiver Grassmannian. Of V-dimensional quiver Grassmannian of a certain finite dimensional representation of this quiver with relations. This means this quiver. And then consider some generating function. They introduce some variable, maybe times y of b. So this is equal to the so-called Q character of Kirillov-Resetsky modules. Of UQ of L. Or they only consider BCFG case.
And what happens if it's simply raised and already?
Oh, yeah, but simply raised case, even for simply raised case, this is something new because, I mean, Kirillov-Resetsky module is a simple module, irreducible module, and so the construction by equivality just gives the the so-called standard module, which is a tensor.
With this quiver, it's not.
This is, I mean, even what is this in this case? I mean, something like this, the ordinary, and just goes. This is one.
Quiver,
it's not a standard quiver, but we're very close to the graded quiver. But in general, this even Kirillov-Resetsky module is more general than the standard module. I mean, it's not different from the standard module. If this is, so it depends on the choice of vertex and also integer. I don't remember what is the standard notation for this integer, but if m is equal to 1, then this is the so-called fundamental module. And the standard module is a tensor product of fundamental modules, and the Kirillov-Resetsky module is a simple quotient. So in that sense, even in this symmetrizable case, symmetric case, their construction is new.
But is it generalized some of your old work? And you also had some older work like this.
Yeah. But I mean, we can understand the Kirillov-Resetsky module in some way, but not not the statement. It doesn't give this kind of statement.
You said that the standard is the quotient of some tensor power of this for m equal to 1.
Standard module is equal to tensor product of fundamental modules. So fundamental module is that m equal 1. So I must explain the what is the spectral parameters, and there's some stories. So I don't want to go much into detail about this representation of quantum affine algebra. And the Kirillov-Resetsky is, in general, this is quotient.
Oh, I see. Okay.
So this is irreducible.
All right.
Okay, I finish the first review part. Any question? Any other question? So I switch to the Coulomb branch side. So I start again. So this, I just erased it. So this is a quiver associated with Fij, which I just erased. So Fij is GCD of minus Cij and minus Cji. So this is equal to, by definition, F. So, of course, this diagonal, so there's no self edge loops, and you just draw Fij arrows between I and J. And I consider.
I think before it now it is by Gij.
Oh? Sorry. This is Gij. Yes, thank you.
Do you assume that the DI are primary?
No, I don't. In fact, the construction is Coulomb branch is independent of the DI, just depending on Cij. In this GL's construction, DI appears only in the truncation order, and the important part is that this kind. I mean, I just erased that this relation between the different linear maps in different patterns. And I consider Cij. So this Cij or Fij. So this is relation C minus Cij. So I check. Yeah, this is additional data.
So when you say quiver associated with Gij, do you mean that this is just the number of edges between two vertices?
Maybe I just. And I take some orientation.
Same for all of them, is it correct?
Yeah, same. Yeah, that it's not so important, but yeah, for simplicity. Yes. So then the Coulomb branch. Yeah, I'm not sure, so I should call this to be Coulomb branch. And so this is some branch of some vacuum of some gauge theory. So I think this is a quiver gauge theory is still this, and I add this additional data. So this is a variant of quiver gauge theory, or a quiver gauge theory with additional structure. So anyway, so I define some space, some variety, affine variety, as spectrum of equivalent Borel-Moore homology of some space, as in the usual case of Coulomb branch. And here GO is product of Q0 of GL. So I also take the so here this is complex vector space. So finite dimension. GL3I of GI. So the only difference from the usual case is, so in the ordinary case, we take GI to be, all the variables to be common, but it could be different for each vertex. And R is a variety of triple modified version of the variety of triples. So first ingredient is vector bundle EI over the formal disk DI. So this is spectrum CGI. So the difference is that from the usual case, we take the same formal disk, but this could be different for each particle. So that is the only difference. The second ingredient is framing. So this is phi I, EI restricts to the punctual disk to the trivial bundle of DI, tensor with this VI. And third ingredient is linear maps, homomorphisms. So AI is of DI, tensor double I to EIs, so homomorph. And Sij for J to I. So I choose orientation here. C of Gij, tensor home of pi ij star of Ej to pi Ji star of Ei. So because Ei and Ej are living on a different disk, so you must somehow, in order to consider the homomorphism between them, so we must move to some compress, but that we give this pi ij, which is covering map, ramified covering map. So pi ij is coming from dj to d, and pi ji is map from di to d. So I just map dj to the power f ji and gi to map to g to be fij. And this is the homomorphism over the formal disk. Okay, and then we pose the condition as usual. So we compose this homomorphism with framing, and that extends across the origin. So that means phi I times AI, and also pi ji star of phi I times Sij times phi I extends zero D, or for the first one. So this is the condition.
And is it really F, Gi, or G, Gi?
So this is F, this is F, this is F. G is, I mean, Gij is symmetric. And Fi, so this, I mean, for example, so this is, one of Fij is equal to 1, F of Ji is 2 or 3, something like that. And this is a slight modified version of affine Springer, total space of affine Springer fibers, and you have the convolution product, and this gives multiplication on the equivalent homology. So once you have introduced the correct definition, all the remaining part is as usual with the ordinary Coulomb branch. So H stamp has the convolution product. And the commutative. And finitely generated. And etc. etc. So basically all the properties which we established for the usual Coulomb branch remains to be true in this setting. So this is somehow we are a little surprised that this just a simple modification realize almost the same thing, but that should be corresponding to this non-symmetric quiver gauge series, and also quantum deformation, quantization, non-commutative. So, but as I said, the disk could be different for each vertex. So, the loop rotation could be different for each vertex, and normalization is just given by the definition is just given by this out di. So, if you multiply by di, then this is compatible with this action. Okay, basically that's it. So I give any question for the definition?
You said a modified version, so it's not.
If di is all the same, then this is the ordinary version, which I mean. We gave with the Mission assertion so that we deal with the quiver for the usual case.
Okay.
Do you think this is really the Coulomb branch of some physical theory?
I don't think so. So in fact, I gave already talk on this talk at IPMU, and Horace are quite against about that claim. Somehow, I mean, my understanding, this depends on the choice of covering, and you cannot make sense for arbitrary three manifolds. So that is the reason why it should not be considered as the three-dimensional gauge. That is my understanding. What? How is explained?
The construction of the map from GDI, so says you cannot explain this diagram using the unfolded diagram and automorphisms, or because there's a small here you're quotienting by the small groups. So can you view it like that or not?
Yeah, I don't. Yeah, I don't consider this possibility. So.
I mean, I think the physicists would probably say it was like the endomorphisms of some line operator that you're constructing using these copies.
Yeah. But somehow, how to say that? So line lives in a different place at each vertex. That is not. Yeah. Yeah, usually physicists say that quantum fields, the line lives on the same space-time. So this is different. So that is my understanding for why this is not the usual. Okay, remarks on definitions. So original definition, which is earlier than the BF definition of the Coulomb branch, come from not instead of R, so use moduli space of twisted maps from P1 to Higgs branch or Higgs stack.
By the way, is it easy to see where the convolution product comes from here?
Convolution product is just you consider the so this is so it's a asymmetric definition EI and O of the DI tensor. There's a symmetric definition. You replace this EI1 and EI2. Then you also consider EI3. So instead of homomorphism between this, you consider homomorphism like this. Then you play the similar game as usual. So you have consider triples. How to say? So M of 1, 2, 3, and you can forget M of 1, 2, M 3, 3. Then you have cohomology here and here. Then you pull back to here and to push forward. By technical reason, somehow we need to make trivial one of the bundle to trivial, but so once you go to this definition, then this is the variety looks very similar to the usual Steinberg variety, but because this is infinite dimension, you must be a little careful. But this technical part remains very exactly the same for this modification. So I hope so the ordinary part, people already know that the ordinary construction, so I don't give the detail. But of course, I mean, if you have any question, just ask us afterwards. So return back here. So this is a larger space. So because X branch or X stack has linear maps in both directions, and somehow R is just have the linear maps in one direction. So in that sense, this is smaller. But you must consider the sheaf of vanishing cyclone here, and then by the so-called cutting, you end up with the Borel-Moore homology of this. This is the definition which we take afterwards. So in this viewpoint, so this irredundant slack or GLS, or more precisely, just projective version. Without grading.
So the projected version is about response situation and there are no WIs, right? The projected version kind of
No. I mean that the two ways, two arrows, in both directions.
but no WIs.
Yeah, you can put the double eyes. They don't. But
Use
they,
the projective algebraic exponentiation when they don't have W's, right?
well, but I mean that in this particular situation, this pre-project means I consider the linear maps in both directions. Double eyes.
It's similar to fixing a big projective or adjective module and looking at some modules of that as a in some specific situations, there's such kind of statement holds, but I'm not sure in general. Maybe that only recovers the core of the quiver varieties. So this should be regarded as finite dimensional approximation of this modular space. But I don't claim that their construction should be considered as a target space. So my understanding is that the target space for symmetrizable doesn't quite make sense. But the space of maps doesn't make sense. So this is what we learn from this construction.
In the symmetric case, what do you mean by X
branch stack?
Just mu inverse 0 divided by G, the usual. I mean, you must consider this to be DG stack in this construction. So you must have appropriate cohomology theory on this modular space. That is what I want to mention. So this is the first remark. And the second remark, in fact, so if you read what I wrote very carefully, in fact, so this our Cartan matrix. So if you compare the relation, is in fact the transpose of this Hennenfent and Grassmannian. And it is compatible with geometric Satake. So GLS, as I said, GLS realize U of N of Katsumudi. And we construct, so I will mention that the slice is as a Coulomb branch for F, this finite type, Q is of finite type, or maybe Cartan matrix. C is of finite type. Then this is generalized affine Grassmannian slice. In G of Katsumudi, or BCFG in this case. So, in order to relate to representation, so we must apply the geometric Satake.
So you're saying this is a theorem in the...
Yeah, this is one of the theorem. But the proof is exactly the same as the usual one. Or slightly complicated because the defining relation for this slice is slightly complicated. So in some cases, we must use computer. So anyway.
What do you mean by defining relation?
Defining a relation for this slice. In fact, for affine Grassmannian slice itself, we don't need it. But for Zastava versions, we need to check to show that some So anyway, so this geometric Satake, you get representation of the Lagrange dual group. And so this Lagrange dual group should be compared with the upper triangular part. Should for this appears in Gauss-Leclerc there by kind of symplectic duality. So that means that we must, in the starting point, we must, so at the final part, we must take how to say, so we must replace this by NKM for transpose. So this should correspond to this Katsumudi in symplectic duality. So that means we must replace the Cartan matrix for transpose in this. Okay, so I will give some properties of these Coulomb branches. So first one is the so-called twisted monopole formula. So this is due to Hannanian and others. So it's a kind of, I mean, check for that whether our definition is consistency check for our definition is correct or not. So they propose the formula for character of this coordinate ring of Coulomb branch. So they wrote down some explicit formula. So if you know the ordinary monopole formula, then this is a slight modification as in our definition. It's really slight modification.
But does it mean that the space appears in some physics work?
Yeah. They want to have the for example, a monopole moduli space for arbitrary groups, BCFG, and they just modify the monopole formula a little bit.
So it didn't appear some kind of Coulomb branch, or you only just considered.
Yeah, they add some additional data. This Fij and Fji, which I just erased. So this.
So maybe that was a question you just asked. So if you said that it's not actually a Coulomb branch, why do they have the twisted monopole formula?
But somehow they just have how to say, they don't even construct a space. They just have a formula which should be the character of
why
the.
Why did they put a formula if it's not supposed to be a? You said before it wasn't supposed to be a Coulomb branch.
Oh well, the formula doesn't say much, I guess. So it's how to say, it's starting from the usual monopole formula and some. You modify the formula slightly by involving this extra information.
Why did they do it, though? What was their
That I don't know. That I guess, that is, I see. That is, I don't understand. And I asked Tachikawa, and he said he doesn't know. So.
I asked Ami.
Yeah, because he's not my colleague. So I forget to ask him. Yeah, in fact, he will come to IPM, but unfortunately, I will not be at IPM when he will come, so I cannot ask him.
What does BCFG stand for again?
So this is the Cartan classification. So B.
I see. It's the Cartan.
Cartan classification. G minus ADE is equal to BCFG. Oh, I thought this is common. People say ADE, and what is the remaining part? So B is generalized slice. So which I already mentioned that. So this, if you don't know what is, maybe I don't explain what is generalized slice. So I just don't explain what usual slice. So you consider the affine Grassmannian for the group corresponding to BCFG. So adjoint type. So this is infinite dimensional variety type for each choice of lambda is dominant co-weight. So you have the orbit. So orbit G of, so this is G, different from the previous G of orbit is parameter dominant co-weight, and we did not find this by lambda. And then you consider the closure, and it contains smaller orbit, and slice is the slice to this orbit. And lambda and mu are related by the usual formula. Then I times omega I. So in this case, I think we don't need to impose the diagram automatism, which is trivial in this particular case. And So I assume this to be dominant. So in that case, we have this all corresponding orbit, and the general slice is the usual slice, which I just briefly explained. So that's a transversal slice to this orbit, and then take intersection with this. And if this is not dominant, then you must generalize the definition, and this is called generalized slice. So you don't need to know what they are, but anyway, so this generalized slice still have some relation to the representation theory of Lagrange dual algebra by geometric version of geometric Satake correspondence. See what time? Maybe almost. Maybe C I skip. C is affine version. So this is you have Bohr variety. Version of Bohr variety. So which is established by my student Enrique Afonso. And
but the usual Bohr varieties thought they were only defined in type A, basically.
But you impose some symmetry. So this for classical types. D, maybe D, I skip it. D, E is quantization. So this is again very same as the usual. So I take loop rotation. So as I mentioned, this is a quantization of MC. Then this is related to shifted Yangian for this is a quantization of this for G of BCFG homogeneous Katsumudi. So there's some homomorphism. You have you can. I mean, so there's some more, a little bit more explicit, not just the existence of homomorphism, a little bit more finer statement. But that is basically already known for the symmetric case, and we generalize this such kind of relation to this case. Okay, so that's it. So thank you for attention.